Awesome. And yeah, so again, this is where you can access the Google Colab. All you have to just do is click on the Python file and click on Open in Colab. And everything should be there, good to go. And if you guys have already downloaded the data sets, it's going to look like this, but let me tell you exactly how to do that. So all you have to do is pretend you don't have these two. Like, let's say I don't have this. Let's just delete this for the time being. Just so we can start from scratch, so it's easy to follow along. All you have to do is click over here, upload file. All that should pop up is like your file, all your files, that directory, and you just can click on that on the one CSV file and click open if you're on Mac, or just double click it, and it should automatically go in. Let me know if you guys need any help with that, and it should pop open like this. And then you would just do the same thing again and import the real estate data as well. Let me know if you are having any issues with it, and I will be happy to help. Just let me know in the chat, and I'll be sure to just go over it one more time. If you guys want, you can give me a thumbs up for when you are ready. Or let me know when you guys are ready in the chat, because sometimes it can take a bit of time. But if anyone just joined us, again, I'm just going to repeat it one more time just for everyone. In the chat, we put in the GitHub repo that has the Google Colab. All you have to do is click on this Python file, and it should pop it open. And all you do is open in Colab. And then there are also two data sets, which you would have to download right over here. It's the real estate one and the diabetes one. And then once they download, all you have to do is click this and import them in. Okay, and I will get started. Just 1 second. Just want to make sure everyone that wants to follow along can. But if no one is having any issues, let's get started. So hi, everybody. Welcome to the regression workshop. Today, we're going to be talking about two specific algorithms in the machine learning algorithms. We're going to be talking about logistic regression. We're talking about linear regression. We're going to talk about like the differences in both and how you can code both of them. But these two algorithms are two supervised learning algorithms. So what does that mean? Supervised, it means it has a label, it has a y value, and like if you guys ever took any algebra class, y equals mx plus b, the y is what we're trying to predict, and in supervised learning, you already have that y value. Or for example, let's say you open a data set for like malicious URLs, for example. In a supervised learning, you would have that feature that says if it's malicious or not. But in unsupervised, you don't have that label, so it wouldn't say if that URL is malicious or not. And it would be up to the machine learning model to determine that. But today we're going to focus on supervised. And let's get started. Let me know if you guys have any questions throughout. My associates, again, will be answering to the best of their ability. And if I see it, I will also try and answer. So first and foremost, if you guys weren't here from a different workshop that I did earlier on, we kind of went through the process of data cleaning. If that is something you guys interested in, it is on YouTube, on the Baruch AIS YouTube. So feel free to check it out. I'm not going to go over as in much detail as I did over there how to clean the data, but I will do my best to make sure that everyone can follow along. So first and foremost, what we are going to start with doing is importing libraries. whenever you're doing anything, the first step you always want to do is import libraries. That is just a good sign that like you know what you're doing. And it is just also a common practice. So we are going to run this. So the libraries that we are going to use is we're going to use pandas. We're going to use NumPy, which NumPy is like a numerical Python. Pandas helps with like, for example, like reading in data sets. It just helps with the data preprocessing and data cleaning as well. Matplotlib and Seaborn are visualization tools, are visualization libraries. So creating graphs and stuff like that. And then the main library that we are going to be using today is something called Scikit-Learn library. It has like all the machine learning models that you guys can imagine. It has more than just linear and logistic regression. It also has neural networks, like etc. But today we're only going to be focusing on linear and logistic regression. So over here, we're going to be importing linear and logistic regression. Over here, we're going to also import train test split, which I will go into later in this and why we need it. And then the next one we're going to import is the metrics. So we want to figure out in a machine learning model, how accurate is this, or how useful is this model in predicting what we need? And so we're going to use mean squared error. We're going to use the R-squared score and an accuracy score. And so last but not least, this one I've actually just played around with recently, and I found it very interesting. So I'd love to share it with you all. Yeah, so I'd love to share with you all. It's something called VIF. For any of those that have taken Quant 2020, if not, again, perfectly okay. I will go into detail. If you ever learned about multicollinearity, that's basically what it is. Again, you don't need to know. We will sort everything out. So starting off, we will load in the data set. Again, this is the we're going to be starting off with the real estate data. We're going to be specifically doing linear regression. Sorry, in the chat, I saw someone was having an error. Yeah, it could be that it's not installed on your machine. If you do like pip install Scikit-Learn, and that could be it. So it could be just your machine doesn't recognize it. Usually it's easier to follow along on Google Colab because you don't have to install it in. Like Jupyter notebooks, you would already have to have it pip installed into your machine. So that could be why. So that's why it's preferred to do it on Colab. But let us know if you still need help with it. Yeah, I would just suggest trying on Google Colab. It'd be a lot easier. But okay, moving on. So again, we're starting with linear regression. The first thing we want to do is load in the data set. So we're going to do loading into DF. We're going to do read the CSV, the content from here. If any of you are running into an error here, right on this first line, it could be that it is not, I accidentally renamed it. If that is the case, if you run it and you're running into an error, all that means is the file is not named correctly. So if you guys have something like this, it's not going to run, for example, because this file doesn't exist. But you see over here, because that's not the correct file name, it's obviously not going to download. So all you just have to do is just remove that in the middle and it downloads in. And the first thing that we always want to do is we always want to see our data. We want to see what we're working with before we start doing anything with it. So df.head, all it does, it just checks the 10 values. And so over here, we can see just an overview of our first data points, of our first 10 observations. And so over here, we can see, okay, we have 1, 2, 3, 4, 5, 6, 7, 8 columns. We have transaction date, house age, we have distance, number of convenience stores, latitude, longitude, and price and house price of unit area. So if you never know what some of this means, like you can always do some more research on it. I'm not going to go into it. I think they're mostly self-explanatory, but if you have any questions about it, feel free. But let's say you're doing this on your own and you don't know what like what one feature is, you can always like do some research on it, because it's always important to have like some background knowledge on the data set you are working with. But continuing on, the next thing I want to do is I want to check the shape. So all that does, it tells us that we have 414 observations and that we have, as we counted before, 8 features. And so this will become important when we're testing for null and duplicates, or if we ever decide to remove any observations, then we know, okay, like we definitely removed it. So let's say we want to remove one observation, we would want to see the next time we check the shape, it would be 413, for example. And so another thing that we can do is we can check for what the columns are. If it's not really apparent over here, so let's say you have like, I don't know, 36 features, you would not be able to see this in this little tiny box. So it would usually give you like 1, 2, 3 dots and then like the last feature there. So just in case, you do always want to do df.columns just to make sure that you have all the features. Usually it would indicate over here that like, oh, let's say you have 36, you would visually be able to see it. So df.columns is one way we can do it. Another thing that we can do, if you guys want to make it more convenient to use the features than having to type out all these words, you can always rename the columns that you want. You can just do df.rename, and then depending on what columns you want to rename, you would just do columns equals to this. So this is just the previous one that you have, the previous name that you have for that column. And then this is what you would want to replace it with, for example. And so all you would do is this. And you guys can play around with it if you want on your own time, when you have time, if it's something you're interested in. I just thought it'd be good to mention. And then the next thing we're going to do is check for null values, because null values, again, can always interfere with our machine learning model. So we just want to make sure that there are no null values. And so we can see there's no null values. And same for duplicates. Again, if you have like multiple duplicate observations, like the machine learning model is going to run, but it's not going to be as accurate because you're training your data set on the same observation. So you can run into some trouble with that. So it's just good practice to remove any duplicate values. And so I just want to check to see how many unique values we have in each one. Over here, we can see that for this specific feature, basically it's like our index. It just has 414 observations, just like we checked in our shape. So I can already tell that this one is not going to play a big role in what we're going to do. But again, it's just good practice just to see. We can see like we have 12 unique values of transaction dates. So we know that there's only 12 dates that they use. And so, yeah, so you can just take a look over here and check. But okay, so let's get to the heart of actually creating the machine learning model. So I know you guys don't want to talk about statistics and we want to code, but hopefully it can give you some understanding. So as I mentioned before, if you guys have ever taken any algebra class, you probably have seen y equals to mx plus b. And so basically that is what this linear regression and logistical regression does. So in linear regression, it will output a number. So we're trying to find like the probability of something happened for example, and in logistic regression, we are trying to classify something. So we would have, for let's say in logistic regression, that we're trying to, again, the same example I used before, if we're trying to predict if something is malicious or not, we would have a 0 or 1 output. But in the case of linear regression, we would have a number output. And so over here, getting back to the statistics portion, so y is going to be our dependent variable. That the y is what we are trying to find. X is our independent variable, m is the slope, and b is the intercept. So basically, it's the exact same thing as in like and over here in this linear regression, but the only difference is that we're going to have multiple independent variables. So it's going to look something like this. It's going to look like y equals to mx1, mx2, mx3, all the way to mx8 plus b. So all it is just we're having more independent variables to train our machine learning model on. So the first step whenever creating a machine learning model, now that we've done the pre-processing and data cleaning, is we want to create the variables. So we are going to create our y variable, which is going to be the house price of unit area. We are lucky enough that they gave it to us over here. It's not going to be so apparent sometimes, but all the y variable is what we are trying to predict. So we want to predict the house price of unit area. And so we're going to do data frame, and we're going to call our data frame, and we're going to get that feature and store it in y. And then for x, we just want everything but the y. So we are going to drop the house price of units, our y variable, and it's going to leave us with the rest of these variables right here. Number, x1, x2, x3, x4, x5, and x6. And so you also want to make sure that you have axis 1 because our features are vertical, and axis 0 would mean that our features are horizontal. You can try, let me show you actually, if you would run it without it, that would work. It would process it, but then you'd run into an error when doing the model. Oh, or not. But it's just genuinely good practice. When I ran it before, it was giving me errors, but genuinely good practice to just make sure that the axis equals to 1, just because our features are vertical. And so now that we have our variables, our next step is to split our data into testing and training. So all it is our training set is what our data is going to be trained on. So it's the data to create the model, and then the testing set is what we want to test our data on. So like we need to see how our data will generalize onto any unseen data. So like, for example, if we train our model, and it's giving us like this amazing accuracy, but we can see like, if like we train our model, and it's doing so well on only this data set, we want to be able to have the same results. We want to reproduce those results in another data set. So we want to make sure that we test it to see how it will like interact in a different data set. And so the next thing we're going to do is we're going to create the training and testing sets. So we're going to do X train, X test, Y train, and Y test. So we're splitting up training and testing for each variable. And so we're going to use train test split, and that basically all it does, it splits our values and it splits it randomly. So we're going to put X, we're going to put our X data, Y data. The test size just indicates how much of the data we want to save to test. So we want to save, in this case, we want to save about 30% of our data so we can test it. And then all random state is basically just randomizes your data. So in the future, if you do ever want to reproduce the same exact, or if you want to use the exact same data set in the future, you set this here. So it doesn't really matter the number. There are some jokes in like the community of like certain numbers over here, but really any number that you can put is going to be helpful. Sorry, not helpful, but it doesn't matter what number you use. All it is so it helps us reproduce the same data set. Something interesting I actually also recently found out is that if you do stratify, this is a parameter that you can also use, stratify equals to y. Basically what it will do is it will use the exact same balances that you have in your data set. So I believe I talked this in the previous workshop, so let me just like go over it a bit. When you have like your classes, for example, like yx, and let's say you want to keep that same ratio that you have for each single data set. Maybe this one is not the best example, but let's say you have fraud values and not fraud values. Let's say you have like a solid ratio of like, I don't know, for example, let's say 50-50, 50 fraud values, 50 not fraud values. And you want to make sure that the data set retains that ratio. All you would do is add this parameter and it keeps it. It doesn't fix any class imbalance. Like let's say if you had like 70 not fraud and 30 fraud, it doesn't fix the class imbalance. All it does, it just keeps the ratio. So that's just something fun to note if you do ever want to look into that. But for the sake of our workshop, we will not be using it, but it is something fun. Let me see if you guys have any questions so far. Yeah, let me pause and let me check to make sure anybody has any questions. Yeah, I was actually learning that in one of my programs. If you guys ever want to check out CUNY Tech Prep, I'm in that. They also I'm also learning all this as we go. So he was mentioning that you can do stratify equals y. It was really interesting to learn about because I've never seen it or heard it before, especially when starting out. So it's just a fun little tidbit to include. But okay, if nobody has any questions, if you do have any questions, again, put them in the chat. We will answer them. But yeah, okay, so moving on. So now we can actually create the model. So the first step when creating the model is we're gonna use the model object, linear regression. We are not using any parameters for the sake. I know in the previous workshop, I was mentioning something called hyperparameter tuning. All that is like playing around with the parameters in like the model in this model, for example, like for certain ones you have like max iterations, play around with the number for that, but we're not going to be talking about that. So we're just going to use the plain linear regression model with the default parameters, and we are going to assign that to our LR model. And so the next step that we want to do is we're going to fit the model to the training data. So basically all this is doing, it's choosing M and B from this equation right here. It's just choosing what the M is and what the B is, or intercept and slope. And so we're going to do LR model.fit, X train, Y train. And the next step, now that our model is trained, we want to make predictions on the data set. So we want to see how our model can predict certain on our data, on our test data. So we're going to do LR model.predicts x test, and we're going to save it to this. Now we're going to compute RMSE and R squared. All this is just accuracy metrics that we want to use to see how our data is generalizing and to see how it's actually doing. So let me run this. And so we get a root mean square of 8.7 and an R squared of 0.5. So what does that mean? So basically root mean square is how close our estimated values are to the actual values. And then this one, R squared, is the percent of variance that is explained by the independent variables. Something actually really interesting that I was learning about is that a lot of people can't explain what variance means. It's kind of hard to explain in data machine in the data world for some reason. But in the best way that I understand it is that R squared is how much of our data can actually be explained. And so hopefully that is a little bit clearer, but R squared is just explaining how much of our data is actually it's just how much of our data is actually explained. This is a little hard to explain, but it is a metric that is widely used, so I did still want to include it. But if you want to research it, again, very interesting topic. So over here we can see root mean square. It's okay. It's not bad. I mean, the closer to 0 it is, the better. But it's okay. It's not anything too bad. And over here we can see that about 54% of our data is being explained. So which is a good score. Usually we would try to aim for about 80%, but for just the raw data on its own, it's not bad. And so one thing I did want to mention when I was making this workshop is that I actually try to do accuracy. So let me uncomment that. Can anyone guess, like by any chance? Oh, well, it's not there. Oh, there it is. Can anyone like guess as to why they think accuracy, there's an error with when trying accuracy on linear regression? So this is the error that we were running into. Continuous is not support. Also, oh yeah, and another thing why I wanted to mention to play around with this is if you get a value error, and in Google Colab, they have this really cool feature where you can just click search Stack Overflow and you get you can get some help, which is really interesting. But yeah, and so if you ever have a question about that, but since we have no guesses, let's use Stack Overflow to answer that. It is always good practice. Like if you don't know what it is, Google it. That is what I do all the time. Just Google it. Specifically Stack Overflow saves a lot of my code. So it's a great website to use. But over here, one of the answers is accuracy score is only for classification. Is if you guys remember what I said earlier, is that linear regression is giving us a number, but logistic regression is what gives us what classifies a value like a 0, 1, or true or false. This one is giving us like a probability, for example, and so the accuracy metric cannot be used with that. So that is why we don't use accuracy linear regression. And so as you see, right as we remove it, it goes back to normal. And so we also, this is just printing the results from over here. And so since we always want to try to improve our model, because I'm looking at the results and I'm like, let's see if we can make it better. Because the goal of a model is to make it as best as possible. So let's see if there's some way that we can improve it. So let's take a look. So first I want to take a look at correlation. Because this is a bit hard to look at, I really love using a heat map instead to kind of get a better understanding of like what I'm looking at. Because just looking at these numbers, it's a little like hard to see. But when you use a heat map, it's a lot more like blatantly obvious. Does anyone want to guess what might be a problem? Like what might be a problem with this? If they see any problems in the correlation in the heat map. If not, that is totally okay. This is actually something I hinted at before. If you haven't taken Quant 2020, you probably have never heard about this, but it is something called multicollinearity. All that is when two of our variables are highly correlated. So for example, looking at, let's say like latitude and longitude, we can see that they are somewhat correlated. And in certain cases, this can be an issue. Also looking at, let's see, number of convenience stores and longitude, it's also somewhat correlated. So sometimes we can run into an error with this. But like, yeah, I'm gonna talk about this later, but another example of what we can look for is we can also see the correlation with the Y and the rest of the X features. So looking at here, as I mentioned before, number probably has no effect on our Y. And as we can see here, it has a very, very little effect. So we're going to remove that. And another one that I'm looking at is also the transaction date. It also doesn't have much significance in terms of predicting our house price. So I decided that we are going to remove that. So now I'm going to rerun our model and see what happens. So it's the same as before as we did up there. So let me run everything again. So let's scroll back up really quick. So over here, you can see we had about a root mean square error about 8.7 and an R squared about 0.5. So now let's compare that to our data. So yeah, looks about the same, but we can see that it did go down a bit, and that is perfectly fine. There's something called overfitting your model, where basically when you are creating your model, remember how I say you want to make sure that it generalizes to another data set. When you overfit that, your model can't generalize well into another data set, so it's not predicting, it's not doing very well on the another data set, but it's doing very well on the data set that we were training and testing it on. So we want to avoid that as much as possible. So that could be an answer as to why it went down a little bit, because we also did remove a feature from here, and they did show like a slight bit of correlation, but we know it has no real effect on it. So that's why it went down a bit, which is perfectly fine. But yeah. And so another thing I also wanted to talk about is, yeah, so as I said before, we took away an independent variable, so that's probably was lowered a bit, but more, again, as I was saying, it's like we want to avoid overfitting, so more variables isn't always better. And in this case, it's like, again, very little correlation, don't have much effect on our model. And so another thing I did want to talk about is that there are also different ways to assess accuracy. So as I was doing some research to see like what are some good metrics that we can use for regression, classification, etc. These are just some metrics that you can use. It's interesting. I thought it was just interesting to look at. So over here we're using R squared. In classification, you can use accuracy, for example. We're not going to go into all the metrics to use, but if you did ever want to check them out or learn more about them, it's interesting. But let's get to what I was talking about before about the multicollinearity, and let me explain it a bit more because I feel like I haven't done a good job at that. But what is multicollinearity and why is it important? So multicollinearity is when two variables are correlated to one another, but this can become an issue because our independent variable is not going to be significant enough, and so it can make our model a lot less reliable. And so one way that we can check for multicollinearity is using a VIF score, which is a variance inflation factor. All it does, it measures the correlation between two independent variables, and we can see like how correlated they actually are. And so for anyone interested in stats, this is what it looks like. In mathematical terms, it is 1/1 minus R squared. And so usually a VIF of 5, I believe, or even mainly 10. Usually for our case, we'll use 5, but mainly 10 is when there is very heavy multicollinearity. Stats. But one way that we can actually code this is, I have never used this before. Again, but it is a very important topic that I did want to go over. And so I didn't know how to code this, right? What do I always say? Google it. So I actually took this code from a website called Geeks for Geeks. If you guys have ever used it, it is a really good website. I've been like reading a lot about it. It goes into a bit more about we did not want to log in, but this is the code basically. It goes into a little bit more about VIF, but yeah, it was, again, very, very interesting. I love this website. So okay, so moving on to the actual coding, we're going to want to create a new data frame for VIF. So we will do VIF data is what we're going to call it. And so we're going to create just an empty data frame first. And then, oh my God, my mouse. And then we will import into our feature column all the X columns. We're going to create a new, we're going to create a new feature column, into a new feature, one column, all our X values. And then we're going to calculate VIF for each one. And this was the code that they had in the website. And so we're going to print it out. And so this variance inflation factor is actually what we imported early on. As I've said before, I haven't really used it before, but very interesting. Well, I find it very interesting. Hopefully you guys as well. But basically it gives you the score for each one. And so when you print it out, you get the VIF score for each one to see how correlated it is with other independent variables. We want VIF to be as low as possible. So a high VIF, for example, like a VIF of 5 or 10, like for example 10, it means that the independent variables are highly correlated with one another. So we want it to be as low as possible. So for example, we can see that latitude and longitude are really highly correlated. So we want to, so we can see like, okay, maybe we should try removing them. So like, let's see what happens with that. And so I just did another heat map because I wanted to see it one more time. What about combining them? You can absolutely do that. That is something called feature engineering. When you play around with the features that you have, you can create it into one location variable if you want. You could definitely do that for sure. In our case, I didn't combine them because like, again, there's a variety of things that you can do to test, to like play around with your data set, but you can definitely do that. And so over here, I'm just taking a look one more time at, because we removed transaction date and number. And so this was the one with transaction date and number. So I just wanted to see one more time what our correlation looks like before we continue to alter our data set. And so now I'm going to try to drop high VIF, the columns with high VIF, which was latitude and longitude. So we're going to do df.drop. And same model as before, all we're going to do is run it. And so over here, we can see that root mean square error actually increased and our R-square decreased. So root mean squared error, again, you want it closest to 0 as possible. So we can tell that removing latitude and longitude actually made our model worse. And even our R-squared went down, which means our data is only 49% explained by our data set. So it actually made our model worse. But does anybody want to take a gander as to why you think it made our model worse? I think I mentioned this before. Yeah, it only explains like 50% of our Y variable for sure. So it's like it's not explaining our data well enough. Previously we had about 52%, which is a bit better. But again, we dropped independent variables. We dropped more features that our data could be explained, like our data could be trained on. So that could be why it went down. But we also have to remember something clear. As I was talking about early on, context is very, very, very important. So one reason maybe why latitude and longitude are highly correlated is because they're both distances. So it could be that because this is giving us like a certain location, they can interfere a bit. So that could also be like one example of why it actually got worse. But yeah, so we just have to make like again, I can't tell you specifically what went wrong. Those are like two of my theories as to why it went wrong. As you drop features, R squared yeah, absolutely. And when you drop a feature, R squared decreases. And so usually it's because it could be because like our data is not having enough like our model isn't having it has less features to train on, but it is not necessarily true that accuracy will always go down. When you drop features, usually we would see it go up if it's not like a relevant feature. But in our case, like we can see that it's actually going down, but this is just towards this specific data set, but usually if you drop certain features, you can see the R square go up. But in our case, it is actually decreasing. And so the two reasons as to why it could be is because our model did rely on those features to train on. But as I said before, we don't want our model to overfit, and it could be an issue with those specific features. So yeah. And so you can definitely leave latitude and longitude in, because over here we can also see that they are correlated with the house price, but they also are highly correlated with one another. So again, you have to see the pros and cons of, okay, should I remove it, should I not? In this case, I probably wouldn't, because they are both distance features, so that's probably why they're highly correlated. Or as someone mentioned in the chat, we can also combine them and see what happens. I think that would also probably maybe give us a higher R squared. And that is something you can play around with if you would like. But yeah, but another technique we can also implement are something called PCA regularization and variable selection approaches. So this can all help manage collinearity, not just to VIF specifically. This is just one metric that I use to see what could be the issue with our data set and maybe if there's a way that we can improve it. But these are all a bunch of different methods that you can try if you would like to test it. But you can also try something called hyperparameter tuning, which is playing around with the parameters in, for example, in our model over here. Because all the parameters in linear regression are set to their default, but you can play around with parameters and see what happens. There's also another method for that called crossfold. No, not crossfold. Oh my god, what is it? There's a way you can do it. I'm blanking on it right now, but there's like a couple ways that you can do on playing around with parameters and testing them out. And so, okay. Does anyone have any questions about linear regression so far? Let me give it like a minute. Oh, it was grid search. It finally came to mind. Something you can do is something called grid search, which if you set like the parameters you want to play around with and input it into grid search along with a model, you could actually like play around, and the grid search is going to test all those variations of parameters, and that is a bit that is something to do with hyperparameter tuning. That's why I'm not going to get into it over here. But if it is something people are interested in, I think that would be an amazing workshop to do. It's just we're not going to have enough time with this over here. But yeah, just want to make sure nobody has any questions. Okay, if not, let's get started with logistical regression. So logistical regression is we're trying to classify something. We're trying to classify our y variable, for example. So we want to find if, for example, I know I used this before. I'm just trying to get a reminder, but if we're trying to predict if a link is malicious or not, we're trying to predict 0 for if it's not malicious and 1 for if it is malicious. One of the algorithms that we can use is logistical regression because it's a classification algorithm. So I'm gonna hopefully everybody downloaded it if you guys are following along, but we're gonna be using the diabetes prediction data set right now. And so we're gonna do the same preparation before. We're gonna load it in, check our first 10 variables. Over here we have gender, age, hypertension, heart disease, smoking history, BMI, HbA1c level, blood glucose, and diabetes, which is what we're trying to predict. And so again, testing the same data processing as before. Oh, we have about 100,000 observations and about 9 features. We have, again, as I mentioned before, these are the columns that we're going to be working with. Let's check to make sure that there are no null values, making sure that there are duplicates. And lo and behold, we have about 3,854 duplicates. In this case, we're going to drop them and we're going to check the shape to make sure that, just for the sanity check, to make sure they actually were dropped. And again, checking any unique observations that we have in each feature. So diabetes is explanatory. You have diabetes or you don't. Hypertension, you have it, you don't. Same with heart disease. Gender. Gender, so male, female, other. And so we're also going to check the data types. So usually in a machine learning model, if you have an object data type, you're going to run into an error because it's going to be like, I can't translate this into a float number or an integer, so I don't know how to use this variable. So what we want to do is we either want to transform this variable or we want to drop it, depending on the data set and what feature it is. But in this case, I do want to keep them and I do want to use them. I want to use gender specifically, but for smoking history, I don't want to use it, so I am going to drop it. And so let's double check to make sure we actually dropped it. And so over here, I'm just checking like gender because we saw that there was 3 unique values. So I just want to make sure that I want to see what those 3 values are. So over here, we can see we have female, male, and other, and this is an object. But as I said before, object data types don't really work well with our model. So we are gonna use something called get dummies to fix this. All this does, it converts the object data type into 0s and 1s, and it creates it into how many features there are in the unique. So that was not a good explanation. Let me explain this a little more thoroughly. But for example, let's say we're using gender, right? So get dummies, it's gonna see, okay, we have 3 unique variables. We have female, male, and others. So we're gonna create 3 more features. We're gonna create female, like a gender female, gender male, and gender other. And for each single observation, it's gonna give it a 0 or a 1. 0 for no and 1 for yes. So let's take, for example, our first observation, female. So we have our 3 features now. We have gender female, gender male, and gender other. So for gender female, for that new feature, it's going to give it a 1 because yes, this observation says that this patient is a female. Now it's going to move on to the next feature. It's going to check, okay, is this gender male? We're going to give this observation a 0 because no, this is male. Same thing for the last one, gender other. Is this other? No, we're going to give it a 0. And so it's going to do that for every single observation. Let me scroll down. And there we go. And so now we have that. But what do you guys think that we should do next? Yeah, if the variables probably are very offended. They're probably like, oh my God, how dare you? Yeah, can anybody guess at what we're doing next? It is, I still don't know. I don't know why they called get dummies as the as what they call it. I don't know. But yeah. Okay, so continuing on. Now that we have these 3 new columns. Sorry, my mouse is acting up. Now that we have these 3 new columns, we don't really need this column anymore because we have it, and because we don't want an object column, we want to remove that. So we are going to drop it. But if you don't know what a certain method is called, not parameter, sorry, if you don't know what a certain method does, you can do, for example, let's say I do not know what df.drop is. Not parameter method, sorry. If I don't know what a specific method is, you can just do df.drop ? And over here on the side, you can see that it explains it what it is. So all this does, it removes rows or columns by specifying label names and corresponding accesses, yada, yada. It just removes. We know that, like we've used it before, but just in case you don't know what something is, or like, let's say you've never seen pd.getDummies before, you can do pd.getDummies ? And it'll pop it up. I learned that this is very, very useful, and it should be something that everyone knows how to do. And if it does have additional parameters, it will go down over here to help you explain what are those parameters that you can use. So like if I didn't know what, let me go back up. If I didn't know what the parameters in linear regression are, you can do linear regression ? Something I like about Google Colab is when you hover over it, it'll give you like this already, but you can also do the question mark to check if you don't know something, or if there's some parameters you don't know, you can just do a question mark and it'll give you like help on the side and explain it. It even gives examples, which is really cool. And so you can use it basically with anything, and it is very helpful. So yeah. Okay. And now again, I just want to see what our observations are looking like so far. Making sure that we drop the smoking, the other object data type that we had, which was smoking history, making sure we don't have gender anymore, making sure we do have 3 variables. Everything is set to go. So now we can actually build our model. So let's create our model. Basically, it's exactly the same steps as before. So we're going to create our X and Y variables. Y is going to be the label. It's going to be what are we looking for. And for this, we're trying to determine if someone is going to have diabetes or not. And so X is going to be the rest of the columns that we have. And so now, again, we're going to split our testing and training into testing and training, our data into testing and training. Same thing as before, but now we're going to create our logistic regression model. And so instead of linear regression, it's going to be a logistic regression. Again, all the parameters we're going to use, we're not going to change any parameters. It's going to be to its default stage. And then we are going to fit the model into the training data, same as before. We're going to predict it, and we are going to evaluate it. ignore this for now. This is something again with the parameter. But okay, let's take a look at how our model did. We can see that the root mean square error is about 0.2, which is very good compared to our linear regression, if you guys remember, which was really high. This is excellent. R squared is also, it's not bad, but our accuracy is really good, which is we have a 95% accuracy, which is amazing. But one thing I do want to note is that if you have like a 99, you want a high accuracy, but if you have like a 99% accuracy, probably it means that your model is overfitting. I know it's like counterintuitive because you're like, oh, I want a high accuracy, but a high accuracy means overfitting. Yeah, it's interesting, but it is important to note that if you do have a really high accuracy, double check to make sure it's not overfitting. Most of the time it is. So usually getting like about like an accuracy of like 80% is good, even like a low 90% is good. But always just double check overfitting. But now I'm going to check correlation like we did before. Specifically, I like to use a heat map again, just to check to make sure, like to see. But yeah. Something interesting to note. Now it'll be a little easier to understand codes we have to use. Honestly, no. I mean, that's just my personal opinion. Stats is very helpful in machine learning. So, taking stats course probably would help you understand more of the mathematical side of machine learning. But they're not necessary. Usually when you can honestly learn it on your own, need be. It's just, it takes a lot of practice and a lot of like research if you don't understand something. When I first started out, I was definitely struggling, but I was doing a lot of projects and I was trying to code a lot to understand what is going on. So really, the more you code this and the more you practice it, the easier it's gonna get. One class probably just can't help you. Probably in terms of stats, it can, maybe stats can help you with the mathematical side, but mainly it's like you have to practice. But yeah, and this is the end of our workshop. But just to go over a bit of what we did is that you always, for always, that what you want to do before you even start creating machine learning model is you want to take a look at our data set. You want to make sure that you go through your data set, you clean it and pre-process it. Feature engineering is something we can definitely like focus on another workshop, but that's something you can also do. Creating, I hope you guys did enjoy creating it. I know it's a bit like daunting and confusing at first creating a machine learning model, but if you guys practice and if you guys like try and build models on your own, like on Kaggle, let me show you guys. On Kaggle, they have like if you go into the code, people have done projects on this. So like let's say like click on this one, if it likes to load, you can like see what some people did and you can take a look at how they pre-process data. This one, for example, use standardization. Let's say you have no clue what standardization is, you can always research it. And standardization, I believe, is something having to do with stats. So like if you want to take a stats course to learn about it, you definitely can, or you can learn it on your own, because I feel like in coding, like you have to have that like drive to want to know more about it and do your own research. But yeah, and so this is what this specific person did. This actually goes into gradient descent cost function. I'm going to be honest, I am not the best with math, but I am learning and I'm trying. So yeah, but again, it's like you can learn always something new about this. But also, if you want to play around with the specific code after, something that you can play around with is playing around with the parameters. So let me actually add something here for regression. So let's say you want to know more about the parameters. Do linear regression question mark and look at the parameters. Like you can also see some other methods that they use, but this is kind of hard to read. What I recommend doing is searching up Scikit-Learn, and let's say you want to do linear regression. They have a website showing you all the parameters that you can use, some attributes you can use. I'm not going to go into this, but you can again look into it more. Yeah, this helps explain like what parameters you can use, or let's say you want to do neural networks, for example. This actually can give you like an example on how to use it. So searching it up is my favorite. Is this a fraction? What is going to be taught in stats 4155? I have not taken stats 4155, so I can't tell you. But if someone has, if they wanna help you out with that. Yeah. I know there's an NLP class that I believe goes into this. I know we have an NLP class, not too sure of how much they teach about this, but NLP using neural networks. So maybe you can look into that one, but I'm not too sure about the stats one. But yeah, and so that is the end of our workshop. Hopefully you guys enjoyed. Yeah, let me know if you guys have any questions. Is object-oriented programming used in machine learning? Give me 1 second, guys. I'm not too sure, honestly. Natalia, or if any of my associates want to answer that question. Yeah, there's gonna be a recording on this workshop that we're gonna post on YouTube. Sorry,
Yeah. So for object-oriented programming, in machine learning, we're basically like the object is the model. So yeah, you definitely utilize that.
Thank you, Natalia. Yeah, I'm actually learning object-oriented myself in 3100 right now. So again, I'm always learning too, especially in machine learning. You're always learning with this. But yeah, hopefully you guys like got something from it. If there's any questions you have, feel free to reach out on Discord. I will do my best to answer them. But yeah, again, thank you so much, guys. Thank you so much for coming, and I hope you guys enjoyed. Thank you, everyone. Bye bye.